Welcome to the second video of our quantum physics series. If you haven't watched the first video yet, we highly recommend checking it out first to get a better understanding of the building blocks of the universe. In this video, we'll be exploring the principles of quantum mechanics, including the Schrödinger equation and Heisenberg uncertainty principle. If you find this video helpful, please give it a like and consider subscribing to our channel for more exciting content on the fascinating world of quantum physics. Quantum mechanics is a theory of physics that describes the smallest possible components of matter and how they interact with each other. It's like the atoms of classical physics, but instead of having only three states, solid, liquid, and gas, they can have an infinite number of states. This means that quantum mechanics allows us to predict the results of experiments without having to rely on our understanding of classical physics or any other field. In this article, we'll go over some basic principles you need to know about quantum mechanics if you want to understand how it works and how this knowledge can be used in technology today. What is quantum mechanics? Quantum mechanics is a branch of physics that explains the behavior of matter and energy on the atomic and subatomic levels. It's also known as quantum physics, or sometimes just Q. In this lesson, we'll look at what exactly quantum mechanics is and how it works. You'll learn about some basic terminology such as wave, particle duality, uncertainty principle, and Schrödinger's cat problem, a thought experiment involving two separate universes. How does quantum mechanics work? The theory of quantum mechanics describes the behavior of matter and energy on the atomic and subatomic scale. This is a subject that has been studied for over 100 years, with many experiments proving its accuracy in describing the world around us. Quantum mechanics can be used to explain some very strange phenomena, such as how an atom can exist in two places at once, or how photons can act like particles when they interact with matter. It's important to note that quantum mechanics isn't just about what happens at this level. It's also useful for understanding other phenomena such as thermodynamics, heat flows, or even gravity. The interpretation of quantum mechanics. The Copenhagen interpretation. This is the most widely accepted view of quantum mechanics. It states that what we observe as reality is only a product of our perception and not necessarily how things really are. For example, if you were observing an electron spin at a certain angle, such as up, there would be two possible outcomes. It could have both up and down spins because it's in superposition with itself, or it could only have one spin direction at any given time, classically speaking. However, according to this interpretation, which was originally proposed by Niels Bohr, you couldn't tell which outcome would occur until you measured them directly. This means that these two possibilities exist simultaneously until they're observed quantitatively by human beings like ourselves. The many worlds interpretation. This theory asserts that everything exists simultaneously in multiple parallel universes called branches or threads. Each branch has its own unique set of laws governing how things work there. However, because every universe contains all other versions of itself within it too, the uncertainty principle. The uncertainty principle tells us that it is impossible to precisely measure certain pairs of conjugate variables, such as the position and momentum of a particle. This means that if we try to measure one variable in order to find out how much energy or mass our particle has, then we cannot know anything about its other variable, namely its momentum. The more precisely one variable is measured, the less precise can be the measurement of the other variable. For example, if you drop an object off a cliff with some potential energy, the gravitational force pulling down, then as long as your experimenters don't know exactly where they have dropped this object off at, they'll never be able to predict exactly where it lands. Wave, particle duality, and physical reality. Wave, particle duality is a principle in quantum mechanics that states that all elementary particles and all matter have the properties of both waves and particles. The concept was first proposed by Louis de Broglie in 1924, and it has been used as a tool to explain many phenomena related to quantum physics. The idea behind wave-particle duality is similar to how light behaves on an atomic scale. It travels at different speeds depending on whether it's being emitted or absorbed by its source, an atom. In other words, because electrons appear like waves when observed through microscope lenses, but behave like particles when measured by detectors placed close enough together so that they interfere with each other's signals, electrons can travel through space in straight lines at different speeds, depending on how much energy they're carrying with them. This makes sense since there aren't any boundaries preventing them from going anywhere once they're emitted from one point, e.a.h.a., an atom. When separated from their source by distance greater than some threshold value we call Planck's constant, Hanau 6, 10, 18, AV 110, 34 J per square meter over 1 meter squared area over 1 meter squared area, 8, 10, 19 joules per second squared. Bell's theorem and the non-locality of quantum mechanics. Bell's theorem is a theorem in quantum physics that states that local realism is an inconsistent theory. It means you can't use local hidden variable theories to explain the results of quantum mechanics. In other words, non-locality is a phenomenon in quantum mechanics where it seems like an object at one location can affect another object at another location without any necessary connection between them. For example, if you have two particles moving together on opposite sides of a barrier, such as two basketballs bouncing off each other, then their paths appear to diverge even though there's no physical barrier present. This has been called spooky action at a distance because it contradicts our common sense understanding of how things work when we interact with each other or objects around us physically close by, like those basketballs. Understanding the principles of quantum mechanics is key to understanding how it can be used to create new technologies. Quantum mechanics is a branch of physics that explains the behavior of matter and energy at the atomic and subatomic levels. It's also responsible for some of the most important advances in engineering, technology, medicine, and science since its inception in the early 20th century. It's easy to see how this theory can be applied to create new technologies, from supercomputers that can solve complex problems in seconds or less, to quantum computers that could dramatically improve our ability to handle large amounts of data without wasting resources on unnecessary calculations. Or computations. Quantum mechanics is a fundamental part of our understanding of the universe. It underlies everything from computer technology to what we can do with light and matter. While its principles were first discovered by Albert Einstein and Werner Heisenberg in the early 20th century, it has since been shown that quantum mechanics extends beyond our everyday experience of space and time. These concepts are just the tip of an iceberg. Quantum mechanics is so fascinating because it shows us how fundamentally unpredictable reality truly is. There's no way for us to know everything that will happen before it does. Thanks for watching. We hope you found this video informative and helpful in understanding the basics of quantum mechanics. If you enjoyed this video, don't forget to give it a thumbs up and subscribe to our channel for more science videos. And if you haven't already, be sure to check out our first video in the series where we explore the building blocks of the universe. Thanks again for watching, and we'll see you in the next video.